Actually, I forgot in the other video to talk about why we don't have an expectation operator related with the joint distribution. If you recall, I said here joint, marginal, and conditional probability distribution functions. Now, when you have the marginal distribution function, you have expected value of x, which can be found x fx marginal probability density function dx over the domain of x. When you have expectation of x on some certain value of y, it's going to be x weighted with respect to conditional distribution of x for a given value of y and integrated over dx. Now, when it comes to joint probability density function, we have a density function of two variables. And note that this may be very obvious, but I have seen in some previous years, some students who does that. We have nothing like an expectation operator of x and y, something like this. You have the expectation operator acting on a single variable. So we talk about expectation of x, we talk about an expectation of y. Well, there is expectation of x and y together if you define the a vector, call this a vector v, for instance. There is the expectation operator acting on vector v, but it's not something we are going to consider within the scope of this course. Therefore, expectation operator and also variance operator will be acting only on single random variables. Now you may say, what if we do something like this? X times f xy, and I integrate this dy with respect to dy and dx. Does this mean anything? For instance, I start with any equation, I just seem to make up an integral and see whether this has some meaning. As you can see, it slightly looks like a formulation to find the expectation of x, but let's see whether it is. Fx xy dy, actually, as you can see, this is x and dx separate from the rest of the terms, so you can put it that way: x times fxy xy dy dx. So this term is going to be integrand with respect to dy. We are going to take the integral with respect to dy, then the corresponding term is going to be multiplied by x and integrated with respect to dy. Note that this is actually equal to marginal density function of x. So basically, this is going to be x fx dx, nothing but the expected value of x. So what I want to say is, what I want to point out is that you can use the joint distribution and multiply it by x, but in this form, such that you are going to integrate both over the y and x, so that at the end you are going to obtain expected value of x. Why this is the case? I mean, because when you integrate first with respect to dy, you are going to be converting this joint distribution to marginal distribution. Then when you are integrating with respect to dx and multiplying by x, you obtain the expected value. All the things that I've said also correspond to variance operator, and therefore that's why for marginal and conditional distribution we have corresponding expected operators for joint probability density function. While although there is the vectorial form, this is not something that we are going to consider.